Well, what I was going to do is, this is kind of a standard talk here on a little bit about SETI, what we're doing to search for extraterrestrial intelligence. I think you all know what the acronym means. Anybody who doesn't know what SETI stands for, it's almost my name, but that's a bit of a coincidence. Okay, search for extraterrestrial intelligence. We're looking for ET, and not just life in space. There are a lot of people within a few miles of where you're sitting whose day job is to look for life in space. And most of them are concerned with finding things like pond scum under the surface of Mars. But we're looking for the kind of life that would hold up its side of the conversation. Now, the title of this talk was actually motivated by the fact that I very frequently get asked, as do my colleagues, when are you guys going to succeed? You've been at this for a long time, right? Now, of course, we don't know when we're going to succeed. Nonetheless, people always give an answer to that question. I listen to Frank Drake. He gives an answer. He says 10 years. He's been saying that for 20 years that I know of. Jill Tarter says my grandkids may find ET and so forth, so she's a little more conservative in her answer. And I was giving an answer as well. I'm going to try and give you what might be a better answer, but probably isn't. Let me just first say that the reason that we think that they're out there is partially just a sunny view of the cosmos that suggests that this planet might not be a miracle, that what's happened here may have happened in many places. One of the possible bits of evidence for that can be seen in this photo here, which I made in northwest Australia a few years ago up in the Pilbara Hills. Anybody from Australia, it's not a place you'd normally go unless you're a cow or a fly. But you see some rock there. That rock, there's a business card in the bottom right I put there for scale. That rock is known to be about 3.5 billion years old, plus or minus a few percent. We know that from radioactive dating, which was actually the kind of dating that I did in high school. So we know how old that rock is, and you can see there's some, does this have a laser pointer? It doesn't matter. You see these sort of round shapes here, look like cauliflowers, in the rock. And the question was, what are those things? Are they just geological formations that happen to get ensconced in the rock there, or are they the remains of bacterial colonies, stromatolites, from 3.5 billion years ago? And the consensus now is, it wasn't when I made the photo, but today, the consensus is these are fossilized bacterial colonies, stromatolites. Bacteria themselves don't make such great fossils, although occasionally they may, but the mounds they build, of course, are macroscopic, big enough to be fossilized, and that's what we see here. Now, the point is, you all know the Earth is only 4.5 billion years old, right? So 3.5 billion years ago, which is rather young in the Earth's history, there was already life, and fairly sophisticated life. And that suggests, doesn't prove, but it certainly suggests that life is not an improbable event because it didn't take very long to get it started. Okay, sort of like if you go into casino in Las Vegas and you put a quarter in the slot machine, you know, $10,000 drops out the bottom, you might conclude, well, gosh, that wasn't a very improbable bet. Now, it might have been that we're just lucky, because otherwise you wouldn't be suffering through this, but on the other hand, this is suggestive. The other thing that's suggestive, of course, is merely the size of the universe. This is just one of the many surveys of galaxies of the universe. I don't know how many of you are interested in astronomy, but every one of the dots here is a galaxy. These areas on the left and right here are just areas that were unavailable to the telescope, so they're dark. But in fact, you can see that the universe is fairly homogeneous in a large sense, but rather inhomogeneous on small scales because the galaxies are distributed in filaments and sheets and so forth and so on. That all tells you something about how the universe was born, but the important point is that there's a lot of real estate out there, right? Our own galaxy has a few 100 billion stars, and the number of galaxies we can see is on the order of 100 billion as well. So most of you have multiplied those two numbers together in your head or on the back of the shirt of the guy in front of you. That's 10 to the 22 stars in the visible universe. The actual universe is of unknown size. It might be infinite, it might not be infinite, but in any case, it doesn't matter. It's still a lot of stuff just in our own universe. That's just a close-up of one of these things. 10 to the 11th galaxies visible to our telescopes. Now, the other thing that's kind of new in this business and wasn't known when the first SETI experiment was done back in 1960 is how many of these stars have planets, because you're not likely to cook up life on stars. When I was a kid, which was sometime before the Crimean War, we were told that the way you made planets was to rip stuff out of the sun, that there was another star that, you know, had a sort of a fender bender with the sun. Didn't actually hit it, but it got close, pulled out gas, and that formed the planets. That was a theory that had a long run, even though it turns out that it doesn't work, which kind of ended the run. But if that were the way planets were made, then this is the only solar system in the galaxy, because it's very unlikely that two stars get close enough together to have this happen. You can work it out yourself, right? You all know the scale of the universe. If you reduce the sun to the size of a ping pong ball, that's a project we leave to the students here for the weekend. If you do that, then the nearest other star is another ping pong ball, but it's in Salt Lake City, right? So what are the chances that those two ping pong balls are going to get, within an inch or two of one another, just by the random motions as they move very slowly through space? Obviously, it doesn't happen very often. In the entire history of the galaxy, you might get a collision like that in this neighborhood. So, this was suggesting that planets were rare. Well, we know that's not true, thanks to the work of astronomers since 1995, who have found more than 400 planets around other stars, and they mostly have found them via this technique here. That little cartoon shows you that, well, finding the planet itself is very difficult because planets are dim, right? And they're right next to a very bright star. And the problem for the telescopes is not so much that the planets are so dim, it's that they're near such a bright star. So the dynamic range is enormously great. It's billions to one, and it's very hard to find that planet. There are instruments being designed that can do that, but anyhow, that's not the way it's done so far. Instead of looking for the planet directly, you just look for the slow wobble of the star. I think most of you know how this works. And that graph there shows you, in fact, the first planet around a normal star, data for that, taken up here at Lick Observatory on Mount Hamilton, not very far from where you're sitting. And you can see that, for a couple of hours, the star was moving toward you at about the speed at which your bicycle goes, and then it was moving away at about the same speed and then coming close and so forth. So they found these planets. We found more than 400 of these things. Now, that number isn't really so interesting. What's interesting is to know what fraction of stars have planets, not how many we found. That number just goes up every 2 weeks. Okay? If you talk to guys like Jeff Marcy, I think it's a picture, here's Jeff. You talk to guys like this who make a modest living finding these planets and say, look, Jeff, if you had perfect telescopes, right, so, infinite signal to noise, whatever, what fraction of stars do you think would show planets? And he can make an estimate of that on the basis of the statistics he has so far. And his answer to me at least a few months ago was, well, maybe half, maybe 3/4. Well, to an astronomer, half is the same as all, right? I mean, there's no difference. So if you can get something within a factor of 2, that's really good in astronomy. So that means all these stars have planets, right? So the only question that remains is, well, how many of these are good planets? Because there's a lot of worthless planets around. I mean, look at Neptune. I'm sure Neptune's not big in your life, and there's probably not a whole lot of life on Neptune for that matter. Pluto's probably, if you consider it a planet, probably not very interesting either. So a lot of these planets are going to be like this one. This is a rendition of the planet found around that star that I just showed you the data for, 51 Peg. This is actually a photo I made in my garage with tennis balls and things like that. But never mind, this shows you what it would look like. They're on the order of 1 trillion planets in our galaxy. That's the consequence of what Jeff Marcy had said. How many of them are like the Earth? Well, we don't know. We've never found a twin of the Earth. We've never found a planet that's really like the Earth, one that you could say, yeah, this might have liquid oceans, thick atmospheres, and who knows, Klingons. Right? We just haven't found them because they're very hard to find. They don't make enough of a wobble to find them using that technique, not with the kind of instruments we have today. It's just getting very close to being able to do that. The instrument that will find them is being run right out at NASA Ames here, and that's the Kepler Space Telescope. And Kepler is finding planets by looking for mini eclipses as a planet gets in front of its star. It's the ultimate staring contest. Kepler is looking at about 150,000 stars. This is a really boring job. It does look at 150,000 stars, and every 30 seconds it downloads, the brightness of that star. It just measures the brightness of these stars. Some of them, by chance, may have planets that cross in front of them, and that reduces the brightness by maybe 1 part in 10,000 if it's an Earth-like planet. And if they see that, and then they see it again, and then they see it a third time, now they can compare the intervals and make sure that it's really an orbiting planet and all that sort of thing. And that will tell you the mass and the orbit of that planet. In other words, bottom line, this instrument will do something that no other instrument could ever have done, and that is to tell you what fraction of stars have worlds sort of like the Earth. It's a very interesting experiment, not only because it's going to tell you that, because this is like completely analogous to what happened after 1492, right? After 1492, within 30 years, the Europeans had mapped the globe. You could have drawn a globe in 1492, but most of it was blank, right? You had Europe, a bit of Africa, and some of Asia, but most of the globe was blank. 30 years later, most of the globe was filled in. There were a few things missing, like Antarctica and some, islands here and there, but Fundamentally, it was done. One generation did that. And that's exactly what Kepler is going to do. It's going to answer this question that no previous generation could answer, and no subsequent generation has to answer. You just need to do this once. And it'll say, okay, if it really does find 30 or 50 Earth-like worlds, you can work this out, that means that a few % of all stars have planets like the Earth. The smart money is saying that's what it's going to find. The smart money being those who successfully competed for the project. Okay, so they're all here at Ames. Well, we don't know if they're right, but if they are right, that's what it'll do. And that'll be, of course, rather intriguing. That means, of course, if that's the right answer, then they're on the order of, hundreds of millions of Earths. That number's wrong, actually. It's on the order of billions of Earths in the Milky Way. So maybe most of them are just sterile, but it would be remarkable if they were all sterile. I don't know if I convince you. Now, I want to make the argument here that it actually matters. There's a question that I think matters in this search for E.T. I've tried to motivate why we think they're out there. I'm sort of switching gears here. Because another question you get all the time as well, particularly from the media people, is what do you think E.T. will look like? Right? I just went down to L.A., 3 days ago, whatever it was, to some production house down there to be taped for Animal Planet. Now, I don't know anything about animals except the ones I eat, but they want me on this thing because they want to ask me about the reptilians. Right? A lot of people believe the aliens are reptilians. I don't know why. I said, if the aliens really are reptilians, why don't you just put them in a tank in the corner of the room and feed them lettuce? The reptiles in general are fairly placid because they're kind of cold-blooded and all. But they do ask. They say, so what would the real E.T. be like? And the answer to that question is, we don't know the answer to that question. I mean, obviously we don't know the answer to that question. But I think it matters to think about this. And in fact, this may be more germane to Singularity University than you're probably thinking at the moment. I'll get back to that. I think it matters. Here's an historical example about why it may matter what E.T. looks like. You can say, I don't care what he looks like as long as he sends a signal that we can pick up. So what if he's green, gray, has 4 eyes, 6 legs? It doesn't matter. It might be interesting to know, but who cares? All right, here you see Percival Lowell in about 1900. Now, Percival Lowell was a Boston Brahmin, or came out of a Boston Brahmin family. In any case, he went to Harvard. He was one of the best students Harvard ever had. But on the other hand, it was only Harvard. So in any case, he was interested. He studied mathematics, but he was interested in astronomy. And rather than taking a job at a fourth-rate university trying to get tenure, he just said, the heck with that, I got money, and he just built his own observatory. I mean, why? He could hire himself, and he did. He actually sent people out to find out the best place to build an observatory, something that was, in fact, a new idea. Observatories previous to this were just built in the center of town, right, where the university was, at least in Europe. And that would work back then, but of course, in 1888 or whatever it was, Edison, invented a practical electric light bulb, and that kind of made downtown areas not so good for astronomy. He was told that the best place was somewhere in South America, and he said, think again. I guess, he was worried about the cuisine. I'm not sure. But in any case, thinking again turned up Flagstaff. So that's where he built this thing. He modestly named the observatory the Lowell Observatory. So here he is, dressed in a suit and a tie, sitting in a dark dome all night watching Mars, because that's what you would do in 1900. Okay. He was convinced by Italian astronomers who claimed they saw straight lines crisscrossing the surface of our little ruddy buddy. They called them canali, but that's because many of them spoke Italian. And it was unclear whether they meant canali to be canals or whether they meant canali to be just grooves or geological features. All right? The Italians themselves were very cagey in explaining what they meant. But Lowell was very sure that these were, in fact, canals constructed by thinking beings. And in fact, here's some of his handiwork. Okay, now he mapped hundreds of these canals. He gave them nice Latin names just in case the Martians hadn't bothered. Just to show you what the real Mars looks like, here's a photo of Mars from a contemporary probe, actually, of the same hemisphere. And you can see that the dark areas, the big dark areas, correlate fairly well. What don't correlate terribly well are all those straight lines. And the question was, well, what was happening here? And nobody's absolutely sure, but there seems to be a good explanation about what was going on with Lowell. Because Lowell, right, was confronted with the fact that the people up here on Mount Hamilton at Lick Observatory, they had a bigger telescope, and they did not see these canals. You might think, well, why didn't they just make photographs, and then you could settle the whole matter? But photography in astronomy was a very primitive art at that time. And these were things you could only see when the atmosphere would clear for a fraction of a second, would stabilize, and then you could see fine detail. Your eye was better than photographs at this point. So they couldn't verify it that way. But the people at Lick Observatory said, look, we got a bigger scope than yours, and we don't see these gosh darn canals. And Lowell's retort to that was, you guys are not in Flagstaff. Here's, the atmosphere is better here. Well, I don't know if anybody from Arizona, they can tell me. But actually what was going on here, I mean, here, contemporary astronomy book, there's the surface of Mars, as it was known to be 100 years ago, or thought to be in any case. And it kind of looks like Venice, California. Lowell died in 1916, still believing that the canals were real. And indeed, not only did he believe it, but he wrote books about this. And he was a good writer, in addition to being good at everything else. He was, as they say, claimed to be the brightest student Harvard ever had. But this is an illustration from a book in 1908, and you can see the Martians here at a cocktail party. You can tell the females because they wear, bows and have long eyelashes, which is, of course, true for every species. In any case, here is the explanation best they could tell, because, as I say, by the time Lowell died in 1916, while he believed in this, almost nobody else did. There was a guy by the name of Edward Maunder. Here he is, Edward Maunder. He was, you may have heard of the Maunder minimum in connection with ice ages and so forth. He was a clever sort of guy. But he did an experiment in which he made drawings of, sort of a hypothetical Mars. That's what you see here on the left. And he just put those in the front of a room full of schoolboys. Okay? These were, I think they were 11 years old, whatever. And, of course, they were at various distances, depending on where they were sitting in the room. And he just had them draw on a sheet of paper what they could see. And the kids in the front of the class would draw something very similar to, what you see there. The kids in the back, it was kind of, obviously they couldn't see all the fine detail. But there was a certain distance somewhere in the middle where the boys would connect the dots, right? So that's telling you something about your retina and your brain, which likes to connect the dots. That helps you to find edges of images, and that may help you, catch dinner, right? It undoubtedly has some survival value to see edges. So that's what was happening, and that's what Maunder maintains was happening to Lowell. By the way, they did try this in Flagstaff. They got a beach ball, essentially, and drew some canals on it and put it, down a field, and then they set up a small terrestrial telescope, right? And they mimicked the optical situation of actually looking at Mars, and they had Lowell look through that and try and map those canals, which he did, and he got them all wrong. But, it was once more an illustration of the adage that the boss may not always be right, but he is the boss, and he told them to stop those experiments. Anyhow, so Maunder did it rather independently. Now, my point here is that when we finally went to Mars, of course, these are the Viking lander photos in the mid-1970s, and you have to remember the excitement when these guys plopped down onto the surface of, the rusty, dusty surface of Mars, and they opened up their shutters. Many of you were not around for that, but it was a very exciting time because nobody knew what they were going to see. There might be little green guys waving, welcome to Mars. Could have been lichen. It could have been something. And it was that, okay, which, as it turns out, is dead, Jim, right? Now, Norm Horowitz down at JPL at the time, who was part of the Viking biology team, said that, well, he realized the public and everybody else was kind of disappointed. And he said, well, it could be that there's life on Mars that looks like rocks, but more likely what this is rocks. In fact, we know they're rocks. Okay, so now the point is that sounded bad, but of course today we're sanguine again about the possibility of Martians, mostly from results like this, where you see an orbiter photo of a crater here, and here you see it a couple of years later, and you see that streak there. Something is obviously leached out of the side of the crater wall, run down the side of that crater, and it could be Brill cream, could be talcum powder. Most likely it's just water, okay? And that suggests that if you really want to find life on Mars, the thing to do is send Bruce Willis to Mars with a bunch of roughnecks and have them drill down a couple of hundred feet until they find the liquid aquifers down that we think may exist down there and pull up that muck and look at it under a microscope. Because if you do that outside here, if you drill a hole 2 miles deep and pull up that muck, you'll find microscopic life as well. So that's the thing. Now, my point in all this is only that it makes a difference how you picture the Martians, right? Because in 1900, the way to find Martians was to use a 9-inch refracting telescope in Flagstaff, Arizona. Today, the way you hope to find Martians is send some sort of robotic drilling rig to Mars and go down a couple of hundred feet and have a microscope on board. So your image of what the aliens might be like will affect your strategy for finding them. So I'll get back to that. Now, intelligent life. if you were to grab the next, 10 scientists off the streets here, I don't recommend it, but if you were to do it and ask them, do you think there's life in space? I suspect 9 out of 10 of them would say, yeah, well, that sounds reasonable to me, right? But if you ask about intelligent life, the percentage drops a little bit. A lot of biologists, evolutionary biologists, and this includes Stephen Jay Gould, he would occasionally write about this, were of the opinion that, all you had to do was change a little bit of our evolutionary history and you wouldn't be sitting here, right? For example, a very obvious example, 65 million years ago, a rock slams into the Yucatan, wipes out the dinos and 2/3, 3/4 of everything else walking around the land. Now, if that rocket arrived 10 hours earlier, it would have missed the Earth, and there'd be dinosaurs in Mountain View. And you could say, well, yeah, but the dinosaurs would have gotten smart. And there are people who think that that might have happened. I mean, evolutionary biologists, not just advocates for dinosaur intelligence. And maybe it would, but I did ask once Niles Eldridge, who's an evolutionary biologist at the American Museum of Natural History in New York. I asked him that question. Would the dinos have gotten smart? And he said, look, the dinos had 150 million years to get smart and didn't. What would another 65 million years have done for them, right? Now, that argument only goes so far. You could have said the same thing about, primates, and they did get smart eventually. But in any case, so this is a very controversial thing. This is highly contentious. Just because I give you a million worlds with life, will any of them have anything as clever as the average resident of Sunnyvale? And we don't know the answer. Now, the public believes that, yeah, it's happening. I'm not going to, never mind all this. Well, maybe I won't. Maybe I'll say something about this. I should point this out because I don't know how many of you think that the aliens are not only out there, but they're here, right? That they're 19 species of grays or something like that, right? Buzzing the countryside, occasionally abducting you for experiments your mom wouldn't approve of. Well, that's not a fringe belief, right? 1/3 of the American public believes that's true. And by the way, 1/3 of the public of Australia, Japan, and Europe does as well. In fact, here's the result of a CNN Time poll made in 2002. Do you think a UFO crash landed in Roswell, New Mexico in 1947? 65% of Americans say yes, right? The aliens have come hundreds of light years to enjoy some Tex-Mex cuisine. I mean, I don't know why they're visiting New Mexico, but anyhow. And hundreds of light years, and then the last 50 feet, they make a navigation error and crash into the dirt. Now, certainly could happen, but I mean, that's analogous to you driving across the country and then totaling your car on the driveway garage door, actually. It could happen. But 65%, see, that's not 0.65, but that's 65%. Is the U.S. government hiding the fact that it knows of the existence of aliens? 80% of Americans say yes. Right? The same government that runs the IRS, but nonetheless is able to keep this quiet. Now, even if you like to think that the feds are keeping the aliens are freeze-dried and stacked up at Area 51 or wherever you like, every other country has to be doing this too, unless you think that the aliens only want to visit America, right? So, I deal with this every day. Every day I get phone calls and emails from people who are having difficulties with aliens in their personal lives. And I can assure you that the people who call me up, I mean, some are nutcases. There was a guy yesterday who called from North Miami to say he's in touch with the Lord of the Rings. But he sounded stranger on the phone than he did in email. But most of the people that call me up, I mean, they've seen something. And they're just not very good at figuring out what that something might be. Okay. Part of the reason why I don't think they're here is, interstellar travel is rather difficult. Our rockets go, 7, 8 miles a second. So if you want to go to Alpha Centauri and visit the Na'vi, for example, to buy some unobtainium, that number is slightly wrong. I think I worked that out again. It's like 110,000 years one-way trip. Okay, so that's a long time to sit there, eating bad food off your lap. But you can build faster rockets, of course. But the problem with faster rockets is they take a lot of energy. Right? If you want to go half the speed of light so you get there in 10 years, you can work it out. Just use high school physics. Forget relativity. Just use high school physics, figure out the amount of energy required. And it's a really big pile of coal. I mean, it's the amount of energy that the United States burns up in a couple of hundred years at the current rate. So it's very energetically intensive. You say, well, we'll just use matter or antimatter drive like they do in Star Trek. And, well, if you can figure out how to store the antimatter, not to mention making it, I mean, I guess you could because that works, but there are other problems. When you're going at half the speed of light through the galaxy on your way to visit the Na'vi, all the interstellar dust and gas is slamming into the front of your rocket, producing high, very hard radiation that zips through the rocket and, essentially kills you right away. But hey, These are all technical problems, so maybe you can solve them. But it's not easy. Now, here's another reason. I just mentioned this for the heck of it. This is like this whole talk. There's another reason why I don't think we're being visited. The question I always ask people who think we're being visited is, why now? Right? Why now? Why are the aliens here just in time to improve your social life by abducting you for these salacious experiments? Right? Why is that happening now? I mean, the Earth's been here for 4.5 billion years. And the usual answer you get is, well, look, the aliens are disturbed by our messing up the environment, or they're unhappy about the fact that we've got nuclear weapons and stuff like that they have some moral interest in us. Now, that's alien sociology, and the data set for alien sociology is very sparse, so we don't really know that. And I say, I don't go in the backyard and separate the ants. You guys have been warring for years, and I just don't like it. I don't bother with that. So I don't know. I mean, but that's all, supposition. One doesn't really know if the extraterrestrials would have any interest in that. But the point is that argument doesn't matter because they don't know about it. Here's I Love Lucy. First episode was the early 1950s. So that signal is like 60 light years out into space. So any aliens that are coming here now because they don't like Fred Mertz's jokes or something, those guys can't be more than 30 light years away because they can't get here faster than the speed of light. Right? So it takes 30 years for the signal to get there, another 30 years for them to respond, come back here. That means that there are only 2,000 star systems that have been exposed to our radar, to our television, to our FM radio, all of which leak off the Earth. Only a couple of thousand stars that are, only half that distance out so that they've had time to come here and haul you out of your bedroom. That's a very small number. The chances that there's any alien civilization in the nearest couple of thousand stars strikes me as very small. So this doesn't work for me. I think it's safe to say that nobody knows that Homo sapiens exists except residents of this planet. Right? Nobody knows that. They know the Earth has life because they could find the oxygen in our atmosphere. That's not much of a trick. They could have done that. And they could have done that 1 billion years ago and found it. Right? But I don't know that they would send their rockets just to abduct the trilobites for breeding experiments that wouldn't work. Then again, I don't know the aliens. Maybe they would. This very controversial thing about whether intelligence is likely, and we don't know. The only way to answer that, whether intelligence is sort of an inevitable evolutionary development or just something that happened here but probably not anywhere else, is either to find it somewhere else, that answers the question, or to figure out how it happened here. Right? Why did we get smart? Okay? And there are various, there are people who study this. Not a lot of them, but there are some. Okay. Now, first off, our definition of intelligence is very simple, straightforward. If you can build a radio transmitter, you're intelligent. Okay, so you should probably ask the person sitting next to you how well they can do it. But I don't know. And so here's a guy, 30,000 years after this photo's made, he's building a radio transmitter, so he's intelligent. And I never hesitate to say, although I've said it many times, that you can tell he's intelligent because he's adding some RAM to his computer there. Okay. Now, there are various mechanisms in evolution that seem to suggest that the development of intelligence is not a very hard thing to do. Predator-prey relations, they ratchet up the intelligence of both the predator and the prey because the stupider prey tend to get caught more often and the stupider predators tend to go hungry every night, that kind of thing. So, gazelles and lions are getting smarter together. There's increased encephalization. This is a plot from Laurie Marino, who's a biologist down at Emory University in Atlanta. And what she's plotted here is the IQ of toothed whales and dolphins, everybody's favorite intelligent species, the dolphins. I think that people like them because they got this smile on their face all the time. But anyhow, now she's got their IQs on the basis of either measuring their cranial capacity versus their body weight, or maybe she's found some fossilized SAT scores. But in any case, you can see this is stupid here and that's smart there. And this is 50 million years ago, and that's today up there. So 50 million years ago, the dolphins were pretty dumb, right? Then they develop echolocation. Their brains get bigger, they get smarter, and then, they do various things. But you notice that some of them continue to get smarter still. Not all of them. Some of them got stupider again. But 2 million years ago, the smartest thing on this planet was a white-flanked dolphin. Okay, probably not true today, but I don't know. So what this is saying is that, look, here's another species from which we... our common ancestor with this species goes back quite a ways. We're not that closely related to them anymore. And yet it was developing more intelligent species, or more intelligent, subspecies. Obviously, other primates have gotten smarter. Dogs and cats are probably smarter than all the dinosaurs. Some birds are pretty clever. They say octopuses are clever, although I've never seen any great literature from octopuses. But still, the point is that not only our species got smarter, lots of them did. And that suggests that there is an evolutionary push for at least some species to develop intelligence. Okay, another idea, and I show this only because it's of interest to young people, is the idea of Geoffrey Miller here. A very clever idea in which he says, look, the reason we got smart was because of the dating behavior of our ancestors, which was to signal for fitness. Right? The canonical example here are the peacocks, right? The males display, the females decide. Right? That's the same for us, right? But it's also true for the peacocks. So the peahens are sitting around, looking at these peacocks, these male guys, and they're walking around, they're showing their big blue feathers. Well, that guy's blue feathers are pretty good, but this guy's blue feathers are better, right? So that one gets taken home to mom. And the question is, what's in it for the peahen to have a peacock with those big blue feathers? Because after all, he only attracts predators, right? And that's probably not a good thing. But on the other hand, he's here. He's made it. He's made it this far. His genes must be good, because that's what she's really interested in. She wants some index into his genetic makeup so that the chicks will be healthy, right? And it turns out, growing those blue feathers is rather metabolically demanding, and if the genes had a lot of mutations, you wouldn't be able to do it, right? So that's the deal. Now, in hominids, we don't have blue feathers, but our brains are rather intimately dependent on how many mutations are in our genome. So if your genome is messed up with a lot of mutations, your brain isn't wired up so well. So the women are sitting around. The guys are passing their brains around all the women. Hey, check it out. And the women are saying, well, Bob over here, he's kind of interesting, but Fred over there, he's more interesting. They're listening with their ears. It's not that they want smart guys like Fred. Right? Women aren't really interested in intelligence as far as I can tell. But the deal is that, fewer mutations. And then there's the other factor, the fact that he's just walking around, right? It's like, this guy attracts predators, but he's still here. I remember all those Clint Eastwood films where Clint Eastwood rides into some godforsaken western town on a horse, and the women all turn out. And you sort of wonder, why? This guy probably hasn't had a shower in 3 months. But they do. The same thing with Captain Cook. He had syphilitic sailors on board his ships, and he would keep them on board the ship so they didn't infect the local population. But the women swam out to the ship. And I asked an evolutionary biologist, why would they do that? And she said, look, they've made it this far. They must be good. Right? So that's Miller's idea that the males' IQ got ratcheted up by women who were looking for fewer genetic mutations. Of course, and that means this guy's very popular. But the question, of course, was why did the women get smart? And his answer to that is, well, they were under a lot of pressure, of evolutionary pressure as well, to be charismatic and interesting, to keep the guy from wandering off. So there you go. All right. Now, the point of all this story, which may or may not be the actual story, Miller thinks it is, and he makes a compelling case. But if this, or anything like it, is correct, then intelligence should be pretty common in space, because this is just a very simple Darwinian mechanism that could obtain on a lot of planets. Okay, the bottom line, we haven't found any compelling evidence of any life beyond Earth, not even pond scum, not even dead pond scum. But we're looking. So how do we look? Well, I'll go through this fairly quickly. One thing you could do is just look for artifacts. This is one of the Apollo photos that wasn't released to the public because, obviously I did this in Photoshop. But clearly this is not, there's nothing wrong with this kind of an approach. You just look for things in space, right, that were left by aliens. And one of the big advantages of communicating this way, leaving a time capsule, is that unlike a radio signal, a time capsule could be there for a very, very long period of time. You don't have to have synchronicity. You don't have to be broadcasting a signal at the right time that somebody with an antenna will pick it up at the other end. This just sits there until they find it, okay? We've not dug up the moon looking for these things, but it's something to do. We could look for, ring worlds or Dyson swarms or stuff like that. All of these things make sense. And there's a little bit of an effort to find these things, not much of one. One could use a better effort. And then, of course, there's the Jodie Foster approach. And this is kind of my day job. We told Warner Brothers this is wrong because we were listening to 56 million channels simultaneously at the time. We said, you have to put 28 million pairs of earphones on, Jodie. They didn't do. There she is at the VLA, which has never been used for SETI, but is very photogenic. And the idea here is that we'll just pick up the signals. And that, this was doing the numbers is a one-line calculation. And that was done by a couple of guys at MIT in 1959. And to their surprise, what they did was they essentially said, what if you took the biggest radar transmitter on the Earth and then the biggest radar antenna receiver combination on the Earth, and you just aimed them at one another, how far could you separate them and still pick up the transmitter with the receiver? That was the calculation. And it turned out to be light years. That was the astounding thing. So this works on paper. Okay. Now, the way you actually observe, this is 10 years ago now. This is down at Arecibo in Puerto Rico. You have a couple of workstations that are doing the monitoring because you have tens of millions of channels and so forth and so on. And also they don't require coffee breaks, and they can integrate up signals and increase the signal to noise in various ways that your eye or your ear could not do. So obviously it's all done by computers. And in fact, you really wouldn't have to sit there once it's all automated. And in fact, it is being automated now. You don't want to actually sit there. That's very boring. The kind of signal we look for are narrow band signals. If the aliens are deliberately trying to get in touch, as opposed to just picking up their cell phones, which would be very broadband, if you just wanted to get in touch, you would put a lot of transmitter energy into a very narrow band, right? Because that makes the signal to noise at the receiving end the highest. So you look for things like this. Okay, those are kinds of signals, by the way, that nature does not make, quasars, pulsars, and so forth. You don't have to worry about those. You never get such a narrow band signal. So you look for very narrow band signals, 1 hertz, even less. Okay, now this looks good. This is right off the telescope down in Puerto Rico, but those are all radar sets, telecommunications satellites, and stuff like that, and you have to sort all that out. Where you really want to put this whole experiment is on the back side of the moon, right, which is perpetually shielded from Earth, but there's certain problems there with cost. Okay, let me point out again that although this experiment is now a 50-year-old endeavor, it's very intermittent. If you add up all the observing time done for SETI, in which we looked at particular targets in the sky, it only amounts to a few months worth of observing. And that's because we always had to use somebody else's antenna, like this one down in Puerto Rico, 1,000 feet across. It's a great antenna, but it's being used mostly for studying pulsars and quasars, pulsars and galaxies. So you only get a little bit of observing time. Well, we're trying to improve that. The bottom line of all this is actually that the number of star systems looked at carefully for signals is fewer than 1,000. It's a very small number. Paul Davies has a book out now called The Eerie Silence, but even he will admit that there really isn't an eerie silence. We've been trying to find ET, and we've barely scratched the surface in terms of the number of star systems that have been looked at carefully. It's not at all surprising we haven't found them so far. But this is kind of discouraging. After 50 years, we still have fewer than 1,000 stars looked at carefully. Well, that's going to change. So here's how. This is Frank Drake, by the way. This is the guy who did the first SETI experiment. Frank just turned 80 last month, or 2 months ago, I guess. And he still comes in the office. He comes in, writes this equation on the board. We're not sure what it means, but there it is. And as I said in the beginning, Frank and the rest of us are frequently asked, when are we going to find them? Now here comes the answer to that. To begin with, we're building our own instrument. It's called the Allen Telescope Array. This is Paul Allen gave the money to get this started. Okay, so the first 42 antennas of an eventual 350 were financed by Paul Allen. They're about 20 feet across. You can see me in this photo. There's Jupiter over on the right. They're about 20 feet across. This is about a 5-hour drive from where you're sitting. If you have the time, you might drive up there and take a look at it. It's kind of a nifty place. It can cover a very wide range of frequency. And because it's an array, you can actually make pixels on the sky wherever you want them, just by, computationally. And that means you can look at more than one star at a time. That speeds up the search. The whole thing that's of interest here is not that this is more sensitive than previous searches. It's not. But it's faster. It's much, much faster. And not only is it faster, it will continue to get faster. This is what it looks like, all 42. This is some sort of plot showing the speed of SETI searches. I just took some index of the speed of our searches ever since Frank Drake's first search in 1960. So these black dots show, the speed. And you can see it's going up. And those of you who are still conscious may notice that this is a semi-log plot. So it's going up exponentially. And, of course, what's fitted here, singularity, is Moore's law, right? Well, it follows Moore's law pretty well because this is mostly digital electronics. So when people ask, when are you going to find ET? Well, look, you're looking for a needle in a haystack, and the question is, when are you going to hit a needle? It only depends on a couple of things. How big is a haystack? We know that. We're looking in the galaxy, so we know how many star systems there are. Second, how fast are you going through the hay? Well, that tells you. And third, how many needles are in there? Well, that we don't know, right? Okay, well, here's some guesses as the number of needles. N gives needle number, okay? This line up here shows you how far out into the galaxy we would be able to search with this thing, assuming it was more or less completed in that year. And you can see 100 light years out, 200 light years out, and so forth. It just keeps going up. But the number of needles is unknown. Carl Sagan figured, probably a million, not billions and billions, but a million broadcasting societies in the galaxy. If he's right, then, by 2015 we might hit one, right? Isaac Asimov figured there were 670,000. For some reason, Asimov was able to compute this to 2 decimal places. But he was brighter than these other guys. But if he's right, then it takes a little longer, 2020 something or other. And Frank Drake himself figures 10,000. Now, these are called estimates, but in this case, estimate is a euphemism for guess, because nobody really knows. But it is true that this range from 10,000 to a million is kind of the range estimated by the people who initiated this whole project, right? So if this project is going to work, if it's going to work at all, it's going to work before you all become middle-aged. And this isn't something that's going to take generations. Either it's going to work in the next couple of dozen years, or there's something wrong. And there could be a lot of things wrong, right? I mean, it could be that we need a lot more sensitivity, or it could be that we're looking at the wrong part of the spectrum, or it could be that they aren't out there, or it could be that they're not using radio, or you can make a whole laundry list of things. But if the assumptions that were made 50 years ago have any validity, have any merit, this is going to pay off in your lifetime. It's going to pay off in the next couple of dozen years. Okay, so we'll find E.T. within 2 dozen years. Soon we're not missing important physics. We might be missing important physics. I also said how we picture E.T. matters. Let me just get back to that because I do think it's slightly relevant for what you guys do. And that's this. We've always assumed that E.T. was carbon-based, complex molecules. There's a periodic table of the elements. There's carbon up there. Carbon, you're made mostly of carbon compounds. Why is that? Is it because there's a lot of carbon out there in the dirt? Well, there is a lot of carbon out there in the dirt, but there's more silicon out there in the dirt than carbon. You're not silicon-based. Could it be an accident? It's not an accident. Carbon has 4 covalent bonds. It's a small atom, smaller than silicon. So, it hooks up. It makes interesting molecules, right? And life is, after all, just interesting molecules. I don't know if you think of it that way when you wake up in the morning, but that's all it is, right? Now you can say, well, yeah, but what about silicon? It has 4 covalent bonds too. Yeah, but it's a bigger atom. The bonds are weaker and so forth. The molecules it makes are not quite as interesting. I mean, consider carbon hooks up with 2 oxygen atoms and you get carbon dioxide, which is kind of useful, particularly if you want to, heat up the earth. You take silicon and you connect it with 2 oxygen atoms and you get silicon dioxide, which is quartz, which isn't so interesting for biology, right? Germanium, even less interesting. Tin-based life. Wizard of Oz, maybe. I don't know. Okay. So we always assume that the aliens will have all these sort of properties that we have. I mean, we could go through them, but these are all just simple engineering considerations. We assume the aliens, the little gray guys or something like that. Here's, Hollywood view of some aliens. This is District 9. These aliens come to Earth. They're just a social problem. Arthropods. And the Starship Troopers, remember Paul Verhoeven's film? The aliens are bad here. And, of course, Hollywood knows that you don't like insects, right? Because, they're annoying. They compete with you for the food supply. They carry disease, whatever. So he figures if you don't like small insects, you really won't like big insects. The aliens are big insects. Of course, scaling laws. If you actually made an insect like this, it would collapse under its own weight, and you'd have to really awful cleanup. But, in any case, this Hollywood's view. Oh, then I love these, the lazy God aliens. Right? This is the only design that works. Any one of these guys could walk into a plastic surgeon in Palo Alto, and the guy would probably say, I can fix that. So I'm sure they could. I mean, a guy like this moves in next door, eventually you'll invite him over for dinner. All right. Now this is your standard alien. And Laurie Marino has pointed out that this is just a projection of what we think we're going to become, right? This is where we're headed. We're losing our hair. These guys have gone all the way on that. Don't have big noses or big mouths because they've lost their olfactory sense and their dentition. And in fact, by this point, the only real jobs are designing websites, so they have big eyes. Okay, well, that's interesting, but it says more about us than it probably says about the aliens. All we're interested in, as far as the aliens are concerned, is that they be intelligent enough to build a radio transmitter. Okay, now that's your intelligence. You got the little 3-pound brain, which runs at about the power level of a fridge light. Okay, I told my brother this. I always called you a dim bulb, and it turns out you are, because... Now, 25 watts isn't a whole lot, but on the other hand, 25 watts is about 1/3 of your entire body power consumption. Your body runs at 75 to 100 watts. Right? So what this means, when you go to In-N-Out Burger, 1/3 of all the calories you eat go to keep your brain warm, despite the fact that even if you're not thinking of anything like most of the guys, right? It just keeps your brain warm, even though your brain is only 2% of your body weight. Very expensive to have a brain. It is. Okay, so that's our intelligence. Now you might say, well, yeah, okay. Let's look at the size of the brain. Maybe the aliens have the same sort of situation. They've just gone to bigger brains because that's what we're going to do, right? Here's a plot of our brain size versus time. So 3 million years ago, our ancestors had half kilo, 1 pound brains. A million years ago, we had 2 pound brains, and now you have a 3 pound brain. Now that last pound was important because when you have a 2 pound brain, you're a forest ape. When you have a 3 pound brain, you get tenure at Stanford, okay? And the assumption here is that, well, maybe our brains will just continue to get bigger. Maybe, but, you know, a lot of objections to that. To begin with, the women will go on strike because they had trouble giving birth to babies as big as their heads are now. You say, you know, you're going to have babies that are going to eventually have 10-pound brains. There are also mechanical difficulties with having a very big brain because, you know, when you twist your head because you want to see what's in the rearview mirror, your head twists off and stuff like that. All these sorts of things suggest maybe that won't happen. In any case, it probably isn't going to happen because of this. This plot, you know, this one's due to Hans Marvich at Carnegie Mellon. All he did was plot the amount of compute power you can buy per $1,000 ever since 1900. And, of course, it's going up exponentially, headed for the singularity, arity. So 19... So you said, right? I mean, a lot of people dispute some of this stuff, but in 1997, for $1,000, you buy the compute power of a spider, right? Today, there's no data here, but in 2010, whichever curve you take here, you buy the compute power of a lizard, okay, if you're selling car insurance or something. And the point here is that by 2020, for $1,000, you buy the compute power of you, right? Now, of course, it's unclear whether that means you got artificial intelligence because it takes more than just the hardware. But on the other hand, maybe the software will catch up. This is all your bailiwick, so I won't say much about this. The point is there's a real time scale argument here. And this is it. And I really don't have to hammer you with this. I just made this little graphic showing the evolution of the horse. What is this? 60 million years ago, a horse was the size of a collie dog. Today, most horses are the size of a horse. Now that's what 60 million years of Darwin has done for him. You look on the right-hand side. I had an 8-bit computer, you know, in 1977. I had to solder it together myself. The computer I have at home today is about, given the bus width and the speed of the processor, I reckon it's 8,000 times faster than what I had in 1977. So in other words, in 25, 35 years, we've had 10,000-fold improvement in computers. In 60 million years, we took a horse from this to that, right? I don't have to hammer you with this. The point is, it's only been 100 years since we invented radio. Right? So imagine the aliens invent radio so they can go on the air and we can hear them. But 100 years after that, 200 years, whatever number you want to choose, as long as it's not unreasonable, they invent their successors. Right? That's presumably what we're doing in this century. Okay? So the idea that you have aliens that are sort of soft and squishy guys like this just doesn't make any sense because that's very unlikely that you just happen to catch them when they're in that short interval between inventing radio and inventing something that's a little bit better. Right? Now, I suggested this up at the University of Washington once, and one of the undergrads said, but well, if you invent thinking machines, won't they kill us? And that's the natural optimism of youth, of course. But I look, I've got goldfish at home, and I don't wake up, I'm smarter than they are, but I don't wake up in the morning and say, I'm going to kill those guys. You know? So I don't know, I don't mean to say, what I'm going to do is when the computers get really smart, I just turn the keyboard around, you know, you type, whatever. That's a whole issue that you all can deal with. My only point is a time scale argument, that I don't think that the aliens are going to be little soft, squishy gray guys. You're going to find some sort of machine intelligence. Now, Kurzweil came to the SETI Institute a couple of months ago. You've all heard from Ray. And Ray thinks they're all going to be, nanobots. It'll be distributed intelligence, that sort of thing, out to eat the cosmos, right? And maybe that makes sense. You tell me. It seems to me that that's a little less likely than putting as much of the compute power as you can into a small space to, minimize the flight time, between different parts of the intelligence. You don't want something way over there when you're trying to think fast. So maybe you just build it all out of computronium, which is from the next moon over from the Navi, I guess. Computronium, the maximally compact computational material, computronium. Ask Ray about it. Hey guys, I don't know. But I do know that if this is true, right, this is, as I say, a very simple timescale argument. If there's any truth in this, the idea that we should be looking for ET on, Earth-like worlds, watery worlds with thick atmospheres and conditions sort of like here, may be very, very provincial. Where would synthetic intelligence go? And I don't know the answer to that. If you know the answer to that, send me an email, because I'd like to know. The only thing I can think of is, and when you ask, what would they find important? Right? What do you find important in life? I know you're all thinking sex and money, but it's actually matter and energy, which, on Earth we turned into sex and money. Okay. Matter and energy, if you want matter and energy, this part of the galaxy is okay, but it's not great. You probably would go to some place where there's a lot more action, like the center of the galaxy, seen in this little infrared photo. Okay? And so maybe we really ought to spend a lot of time looking at the galactic center. It's kind of unfortunate that it's in the southern hemisphere, but hey. Because that's maybe, there's been plenty of time for truly advanced machinery of any sort to get there. And maybe that's where the signals are coming from. Well, I think I'm going to stop it there and allow you to ask those questions that I've deliberately avoided going into because I've spent too long on this. So, is anybody conscious who wants to ask a question? Yeah.
I just wanted to hear your opinion on the WOW signal, and also, do you agree with Stephen Hawking that we should not be trying to contact?
Yeah, the WOW signal. The WOW signal was found in 1977 at Ohio State University. What happened is they had a big radio telescope there that wasn't terribly useful for radio astronomy. So they just used it for SETI. It just sits there, right, in Ohio, in Columbus, Ohio, and the Earth would rotate, as it turns out it does. And, it would just sort of sweep the sky past this. And every morning, one of the astronomers would go into the shack where they had the computers and would look at the printout. In those days, computer output was printout. And he was going through the printout one day, and he finds a signal that looks very much like what you expect from an extraterrestrial source. And he wrote WOW next to it. That was brilliant, to have written WOW next to it, because there have been thousands of such signals, right? But this is the triumph of marketing. Calling it WOW was truly a bold stroke, a brilliant stroke. And it's become famous. It has all the characteristics of a signal coming from beyond Earth, but I don't think it was ET, or in any case, it doesn't matter whether I think it was or don't, because that telescope had a second receiver on it, which automatically looked at the same spot on the sky 70 seconds, a little over a minute, 70 seconds later, and it didn't find that signal. And it's been looked at many times since with much better equipment, never found again. So if you see it only once, you can say, well, I don't know what it was, and maybe it was ET and then he went on vacation. Could be. But that's not science. So that's so much for the WOW signal. The other part of your question was? Stephen Hawking. Yeah. Did you all hear this? It was like about a month ago when the Discovery Channel had this show about Stephen Hawking, and they resuscitated a statement that he had made maybe in one case, I think he may have made this statement 20 years ago, in which he says, well, contact with ET might not be a good idea because consider what happened to the North American natives when the Europeans first visited them. It didn't work out so well for them, and that's certainly something you can learn from our own history. You look at even Captain Cook, who was under orders from the British Admiralty not to interfere with the societies he found in the South Pacific, but nonetheless, he destroyed their culture simply by sailing into their lagoons with these ships that had really nifty things like the wheel, right, and metal and syphilitic sailors and all that kind of stuff. So, they figured whatever mojo these guys have is better than ours, and they immediately became, converted. And, their own culture was subsumed into Western culture to a large extent. So that's all that Hawking was saying, look, beware. And, well, doing SETI, there's no danger there. You're just listening, right? You tune in your local radio DJ, and he doesn't jump into the car and start molesting you because you tuned him in. But he doesn't know that. He doesn't know that, right? But what Hawking is saying is, but don't broadcast anything back, because that's like shouting in the jungle. You don't know what's out there. Maybe it's a very, very small probability that anything malevolent is out there. But on the other hand, do you want to be the person responsible for destroying the Earth, right? Now, I don't buy it. In fact, those of you who want to look it up, if you go to New Scientist and type in my name, you'll find I wrote a little opinion piece about this about 3 weeks ago. And what I said was this: look, you know, you can worry about that. Obviously, we don't know what the aliens are capable of or what they're interested in doing or any of that stuff. And maybe you don't want to risk the Earth. I know it. I didn't note it in there. But, you know, Carl Sagan sent a map of where the Earth is out on the Pioneer and Voyager probes, right? So, you know, it's like a map of the stars home. You know, I'm sure nobody gave Carl Sagan permission to tell the universe where you live, but he did. Those things will never be found by aliens, so it doesn't matter. But a signal might be. And if you find a signal coming in, you might broadcast back, hi, we're the Earthlings, you want to join our book club? We got some used cars, what? You know, you do all that. And he's saying that maybe that's a bad idea. Well, it may or may not be a bad idea, but the point was that we've been doing this for 70 years, right? We've been broadcasting into space willy-nilly for 70 years. TV, 24/7. Also the cities of Earth have these TV transmitters. And you say, yeah, but those signals are very weak by the time they get to the aliens. And that's true, they are. But they're only weak by, you know, maybe 3 or 4 orders of magnitude below what we would be able to detect at those distances. So if you look at the growth in sensitivity of radio telescopes, you see that increases by 2 orders of magnitude per century. If these aliens are capable of mounting an attack on Earth, they can easily pick up this stuff. And in fact, they've already gone just a couple of hundred Earth-Sun distances away from their planet, and they can use their own star as a gravitational lens, which gives them another 10 or 11 orders of magnitude of sensitivity. They can see our street lamps, frankly. And so if you want to really be paranoid about this, that's fine, but it's too late. That horse has left the barn. You going to lose sleep about this? I don't. Any other questions? You want to get out of here, right? Yeah.
Could it be possible that maybe, you know, we're looking for radio signals and maybe because of our development cycle, that's not what the aliens are out there using? Because we're starting to learn that quantum computing, quantum entanglement allows us to begin to start looking at how we can transmit information at a quantum level. So maybe we're just kind of, you know, not advanced enough.
Yeah, well, that's certainly possible. Everybody heard the question? Yeah. Anybody here mind asking whether you heard the question? Yeah, I get emails about that essentially every day. They say, radio signals. We also look for flashing light. Electromagnetic radiation. How yesterday, how 20th century. That may be. But that, you know, it's kind of like telling Chris Columbus, hey, man, forget these wooden ships. You know, just wait a couple hundred years. You'll be able to cross the Atlantic in 6 hours eating peanuts off your lap, you know. That doesn't help him. And it turns out the wooden ships were good enough. The point is this: we don't know. There may be physics that allow some sort of communication mode that really trumps the sorts of things we've thought of, in which case this may be barking up the wrong arboreal fixture. I mean, maybe that's true. But is that an argument to say, well, we just won't do this. We'll sit on our hands and wait for other physics? That doesn't sound like such a good argument to me. And as far as quantum entanglement is concerned, there's something called Bell's theorem. You may want to look it up. It's not clear that you know, quantum entanglement will allow you to actually communicate faster than the speed of light. Quantum entanglement works, but in terms of sending information, it may not beat the speed of light. Yeah. Okay, yeah.
What would be the name of that first digital signal processor, the custom one you had built?
Were you involved with that? Is that what you're asking? Which custom digital signal? You mean the one that we used in the early 1990s?
The original Project Phoenix custom one.
Oh, it's still being used. We use it for the Allen Telescope Array. We're trying to replace it. Yeah, it's still, most of it is still being used. It is. If you're part of the engineering team, I take my hat off to you if I had a hat. The guy behind you.
What about like topology and like the geometry of the universe as a medium of faster than speed of light travel?
Well,
like a mathematical approach, because I mean, obviously nothing goes faster than c that we know of.
Yeah. Well, you're suggesting why don't we just warp space and then we reduce the distance between us and them, and then we get the signal faster, which is true if you have, you know, a black hole at your disposal for warping space adequately to do that. I mean, yeah. Well, we don't. Maybe they do. I mean, that sounds like some science fiction film by Ray Bradbury, or story, right? Yeah. Yeah. Well, who knows? They may do that. I mean, that's sort of like asking, what about faster than light travel? You know, the way to implement that is to warp space. You don't really go faster than light, but you just shorten the distance by creating wormholes. Wormholes, as you know, wormholes work on blackboards. It's unclear whether they would work in practice. I asked a cosmologist about this when I was living in Europe, actually, about that. And I said, do you think you could ever, in fact, use wormholes for travel from one spot in the universe to another, or one era to another in travel in time? And he said he doubted it. He said because if that were the case, then an alien could pop up in the seat next to you, and he didn't think that was a nice thing to do. So his take on it was that it wasn't likely to prove practical, or possible. Practical is a different word, possible. But I don't think anybody knows. If you can work it out between now and next Tuesday, you know. Well, how would we decode the signal? First off, let me point out to you that in our radio searches, it's not true in the optical, but in the radio searches, we integrate for minutes at a time. In other words, we average the incoming cosmic static for a few minutes. That builds up the sensitivities. You can find a much weaker signal. But obviously, it throws away the information. Right? If you took a TV signal, right, which has like a 5 megahertz bandwidth, you take a TV signal, you average it for 2 minutes, well, the picture and sound are pretty much gone away. All that's left is the fact that you know that there's a transmitter, right? There's a carrier. Okay, so we do the same. And if you found that, you say, okay, well, let's just change the hardware a little bit so we can see variations that are occurring at a microsecond level or a nanosecond level. But now you don't have the sensitivity. In order to do that, you'd have to build an instrument that, in the case of a TV signal, would be 4 orders of magnitude bigger. So that's a very much bigger antenna. But on the other hand, all of this, which is privately funded, completely dependent on people like you, right, to fund it, I think you would get the money to build that. Yeah, very quickly. Okay, so let's assume that happens. And then they get all these bits coming down. And so the question is, what do you do with them? I mean, there are 2 approaches. You could just, turn them over to some experts. It sounds like the Dead Sea Scrolls. But we still don't know what the Dead Sea Scrolls said, so, or you could just put them out on the web. Everybody download them to your hard drive and work on it. And I'm not sure that you'd ever figure it out. I mean, who knows? And would Neanderthals ever figure out a digital television signal? Probably not. Even if you gave it to them, it's not that they were stupid, but they probably not figured out. And somebody suggested to me, after 200 years of trying, people would start worshiping these bits. I don't know. I don't know if that happened or not. I mean, if they're trying to make it easy for you to figure it out, then maybe you would see pictures and things like that, and a dictionary. Who knows what they'd do? But I think in my opinion, the best thing you do is just put it all out there, let everybody try.
Yeah, but there's no sort of systematic way of looking at this. I mean, to let everybody try is a little bit.
Well, letting everybody try means that you also let the experts try, insofar as they're experts. I mean, there are people who are good at pattern recognition, there are people who are good at decoding things. They'd be amongst those people that got hold of it. I mean, you think about it, the hieroglyphics were decoded very quickly by Champollion in 4 or 5 years. Now, mind you, he was expert in he also had the Rosetta Stone and all this stuff. But they would have figured it out anyhow, even without the Rosetta Stone, because there was so much of it. There was enormous redundancy. There was a lot of material. Right? There's some codexes from Middle America that have never been figured out because there isn't much material. Right? So it would help to have a lot. I mean, people ask, what should we broadcast to the aliens? And I even wrote a paper on that. I mean, a lot of my colleagues say, well, we ought to use mathematics, or we ought to send them our best music, or we ought to send them, our noblest achievements. The heck with all that. I wrote the paper and I said, send them to Google servers. Just send them everything. Somebody said, but there's a lot of porno on that. I said, well, so what? You think that the aliens would be offended by human porn? God, nude humans, Zork. What do you think? But send it because it's so redundant. There's so much redundant information that they'll figure a lot of it out. That was my suggestion. But nobody knows. This is a problem down the road. You look familiar. Yeah. I saw your cousin once, yeah.
If and when a signal is discovered, what is or is there a protocol for notifying the general population of the planet that, hey, we've got some buddies, or not buddies?
Okay, all right. You forced me to show these last slides. There is a bottle of champagne at the observatories. We always keep it there. It's really there. I made this photo down in, in Arecibo in Puerto Rico, but there's one at the Allen Telescope Array too. Excuse me. Every time I go to the observatory, it's a different bottle of champagne. It's there. But actually, when you actually get a signal, nobody thinks of it. I mean, everybody figures it'd be a big cover-up and all that. This is a photo I made at the S.E.T.I the S.E.T.I Institute back in 1997 in June. This was made at 3:30 in the morning, and we were following a signal that looked like it was the real deal. If any of you still have an interest, by the way, in this subject, despite this talk, I have a book called Confessions of an Alien Hunter, and I begin with this signal because it was sort of interesting. It showed what happens if we actually get a signal, because we thought it might be the real deal for about 16 hours. Turned out it was the Soho solar research satellite. The signal was bouncing around the steelwork of the antenna just the right way to mimic ET. But there we are at 3:30 in the morning, and nobody's going out to In-N-Out Burger, and nobody's going home to go to sleep. We're just sitting there glued to these monitors, right? At 9:30, the star had set. We had to wait 12 hours before we could see it again. And I was sort of half asleep at my desk, and the phone rings, and it's the New York Times, right? They already knew about it. There's no secrecy. There's no policy of secrecy. So what would actually happen is that the media will be all over it. And, of course, the more responsible media will wait until you've confirmed the signal is truly being extraterrestrial. And that might take you a week. But the Weekly World News, the checkout line press, they're not going to wait. So you'll read about it first at Safeway or at Lucky. That's for sure. Yes, you.
So actually asking the reverse of Connor's question, what if, this is assuming that whatever signal was intercepted by SETI.
Yeah,
what if there was some crazy UFO person who actually did intercept a signal? How would they even know?
I appreciate your implication that the people at SETI are not crazy and wacky. Yeah. Well, we've seen that happen, actually. What if it's somebody out there, just the great unwashed, right, that find this signal? That could very well happen. And very often, there's a lot of precedent in science for discoveries being made by people who weren't looking for what it is that was discovered, right? Penicillin, whatever, X-rays. That could happen. There was I think it was 1999 or 2000, there was an internet claim, a claim on the internet, some guy's website, by an amateur astronomer in the UK who said that he had secretly used his employer's dish to look at the star EQ Pegasi and had found a signal, and he was publishing this. And, I was driving home from, I had given some talk down in Monterey or something. I was driving up 101 the night that this story broke, and I was listening to Art Bell. I don't know if you know Coast to Coast AM, this late night show. And he was saying, I wish Seth would call me about this. And I nearly drove off 101 when I heard it. And I got home, my wife said, Art Bell's been calling you. And I said, I figured that. And I went on, and I said, look, it looks like a hoax to me. Well, for a week, there were all sorts of efforts to figure out whether this was a hoax or not a hoax. And it even led some people in Australia to actually use radio telescope time to go verify this thing. It was a complete hoax. It was obvious that it was a hoax. To me, it was obvious. But you could say, but what if that had been real? That's really your question. What happens then? Well, it's a little trickier, but it'll get out. Somebody asked, I didn't get to the protocols. There are protocols here, actually. In fact, I'm the guy in charge of the committee that's revising the protocols, all of which is highly emotional. But the protocols don't have any force of law. They have only minimal practical benefit, and all they say is this: if you find a signal, you verify it, you tell the world, and you don't respond to it without international consultation, whatever that is. And I often ask the committee members, I say, what is that? If you talk to the Swedish chess team, is that international consultation? And nobody knows. Nobody wants to say UN because they figure the UN couldn't make up their mind soon enough, or maybe there won't even be a UN when we find the signal. But international consultation. Look, the only point of that was to assure other countries that if, say, the U.S. finds a signal, we're not the only ones doing SETI, but almost, if the U.S. finds a signal, that they won't hog the information. But look, and this kind of answers your question too, if you find a signal, this is not like, stashing away the evidence at Area 51. You can't do that. The signal's up in the sky. Anybody can get to it. Anybody can get to it. And I think that's an important point.